Hydrogenation of alkenes is another great alkene reaction where we take an unsaturated double bond and we convert it to a fully saturated simple alkane. And this is done with hydrogen, and then usually you'll see platinum or palladium on carbon. And in lab conditions, this is also usually done at pressure, some ranging from just a balloon of pressure filled with hydrogen gas to other times you have like it incredibly pressurized. And that's why I'll walk you through the mechanism later, but remember that you need pressure. That's going to help you realize why I remember the mechanism the way I do. So the really straightforward answer down, if you just have a simple straight chain alkene and you see this H2 platinum on carbon, just go draw the structure again, erase the double bond. There's your answer. It's actually that easy. This one should always be getting right on your exams. However, you need to remember this is syn addition, so it's stereo specific. So say we have something like a ring here, okay? And we have 2 chlorines here on the end of our cyclopentene. And we're going to hydrogenate this with H2 palladium on carbon. So what are we going to get? We're going to get our cyclopentane for one. Cyclopentane. But remember, I said this is syn addition, so that means the hydrogens came from one face, the same face. So there's a 50-50% chance of it coming from the front or the back, and it technically doesn't matter because this would be a racemic mixture here. But I'm going to say for our cases, it came from the back. So our chlorines get put on wedge bonds, which remember the wedge bonds mean they're coming out at us, and the dash bonds mean they're going away from us. So this is our structure. We cannot simply just write this right here. Should I give that? Hold on. That's not the best cyclopentane, but we cannot simply just write this. Technically, that is what that makes. But because there's stereochemistry here, because this is a ring with fixed rotation, this does not accurately describe the resulting product. Now, when you have a straight chain alkene or alkane, there's free rotation. You can generally get away with that. But if there's stereo centers involved, you need to be careful. And so you should always show the stereochemistry when you're doing a hydrogenation, even if you don't really need it, unless it's a straight chain like this. So now let's go through the mechanism. I'll be honest with you. I never learned the mechanism when I went to undergrad, I don't think it was really harped upon that much, other than just to know that it was syn addition, or whether it was just not really explained, or maybe I didn't know. But even when, I go in my textbook that I use, it's not really in there. And I've seen a couple different mechanisms online, so I'll just walk through it here. So say we have this alkene right here. We're going to hydrogenate it. I've seen some mechanisms where it is simply this easy. We take this comes here, and this goes there. And we get there's 1, 2, 3, 4. We get our alkene. Okay? And remember, we should be showing syn addition. So realistically, it should be looking like this. We're going to pick a side. Okay? That's a terrible wedge bond. To show that. And in reality, we should fix this then too. I've also seen some where instead of a concerted reaction like that, we have a kind of halfway. This is the metal surface, by the way. This forms a metal hydride. I've seen some where it says our alkene coordinates to the metal, and then that forces one bond up, and we get kind of a half where it's still bound right here, and then we have our double bond and our H. There's still one H over here, and this goes here, and this comes over, or something like that. Some places don't even show like actual reaction hours. They just kind of show the different steps. So I would check with your professor as to which one they prefer, which one they want to see in your exam. But the way I always saw it is because, remember I said this is performed at pressure. Sometimes just the pressure of a balloon. Other times the pressure of like a couple atmospheres. Now I have our double bond. Ooh, that's terrible. Now remember this is under pressure. I always imagined it as, because pressure is pushing all these molecules together. We have a metal hydride surface. Metal. And then this just gets physically pushed down onto it. Okay, so these just get smushed onto this to then force this to be syn addition, because there's just no other way, because they just got smushed on there. That's why how I think of, if we do it with the ring example with the cyclopentene, think of, I'm no artist, okay? So cyclopentene is actually kind of like this. Here's our double bond right here, okay? It's not I'm gonna say this is not to scale, not to actual. So we have our chlorines out like this. Hydrogens just come in from our metal, and they just get pushed right onto that, and they physically push these chlorines down, or they came in from and physically pushed these chlorines up, and then that gives us our cyclopentene, or pentane now, where our chlorines are down, and we have up hydrogens, or vice versa. Now it's important to remember, because you're going to be thinking stereocenters, like I said. Remember something like this? If we create this product, you're saying, as I said, there's a 50-50 chance it comes in from the front of the back. So I usually just choose to put it on the chlorines on wedges, because that's just what's easiest for me. Say, okay, well, what if I put the chlorines on dashes? That's the enantiomer, right? Well, actually, no, because of something we'll get into in another video known as stereochemistry and racemic mixtures. And essentially, these have an internal plane of symmetry. Therefore, while these are each chiral centers, they are overall achiral molecules. And actually, if you wanted to think about it, these are actually the same molecule. Because remember, this is coming out at us. These are going away from us. If we took this molecule like this and just flipped it 180 degrees this way, these dashes become wedges, which is exactly this. So you don't have to worry about enantiomers when you have a symmetric ring like this for something where you're doing a hydrogenation. But it's always good practice to, you need to show your stereochemistry, because there's that fixed rotation, or rather lack of rotation on the ring. So you always want to share your stereochemistry. And if you want to get more organic chemistry learning, hit that follow button.